In this video, we are going to look at formal charge, and I'm going to just grab some rules here to help us with that. Okay, I'm going to grab a marker and I'm going to look at two examples of drawing a Lewis structure for CO2, carbon dioxide. I'm going to maybe just sneak this down here a little bit. First, I'm going to do electron count on carbon dioxide. Carbon has 4 valence electrons. Each oxygen has 6 for a total of 16 electrons. So looking at these two instructions, we have, or these two diagrams, we have 8 electrons here and 8 more electrons here for 16. We also have 8 around oxygen, 8 around this oxygen, and 8 around this carbon. So we are good with the octet rule for all 3 atoms. Let's look here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons, 8 around this oxygen, 8 around this carbon, and 8 around this carbon. So we are also good with the octet rule here. So both of these models fit the Lewis structure rules that we have, and they both seem to be effective models, except one is preferred over the other. And here's how, when we have two viable structures, to predict the one that would be preferred over the other one. First off, you have to use formal charge to do this. So in order to do that, you take the sum of the lone pair electrons and then half of the shared electrons, and that's the number of valence electrons assigned to that atom, and then subtract that number from the number of valence electrons on the free neutral atom, which is the number you get by just looking at the periodic table and seeing what family it's in. So let's just show that in action. And what I have here is oxygen. We'll start with the family it's in. It's in family 6, so it has 6. I'm going to minus the 2 out of the 4 shared electrons. So half of there's 4 shared electrons, but I only take half of those. 2 are assigned to oxygen, 2 are assigned to carbon. So 6 minus 2, and then minus these 4 unpaired electrons gives me 0. It's going to be identical over here, so that'll be 0. And then the carbon, I have 2, 4, 6, 8 electrons, but only 4 of them are assigned to oxygen. I'm going to subtract that from the original 4, and that gives me 0. So everything here has 0 formal charge. How does it work over here? I can look at the oxygen, and I can say, oh, it has 2, 4, 6 shared electrons, so actually 6 shared electrons, so we take half of that, that would be 3. This one has a lone pair, which would be 2. 6 minus 3 minus 2 is plus 1. Over here with this oxygen, it ends up being what? 1, 6 minus 1 minus 2, 4, 6 gives me a minus 1. And then I get carbon with 0. Okay, I look over here and I say, all right, what's the difference? These are all zeros. This is a plus 1, this is a minus 1, and the 0. Now, the sum of the formal charges of the atom in a given molecule, Ryan, must equal the overall charge, okay? And it does here, and it does here. It says, if non-equivalent Lewis structures exist for a species, those with formal charges closest to 0 and with any negative formal charge on the most electronegative atoms are considered to best describe the bonding in the molecular ion. So this one has the charges closest to 0 compared to this one. So this one here is considered the more viable or the better model for what we have. Let's look at another example. And I'm just going to scroll down here a little bit. And I'm going to look at POF3. And I look at this and I say, okay, 5 valence electrons here, 6 valence electrons for oxygen, 3 times 7 is 21 for fluorine. And I got 32 total electrons. This is one structure, 8, 16, 24, 32 total electrons. Looks like I got 8 around everything, so we have no violations of the octet rule. Okay, if I look at this in terms, and let's look at this one here, I got 8, 16, 24, 32 electrons. Okay, I do everything right except I violate the octet rule with phosphorus. Remember, phosphorus is family 3, and it can violate the octet rule if it goes if it has those empty d orbitals or tends to use those. So this is a possibility, even though it violates the octet rule. So let's look at formal charge on each of these. All right, so phosphorus, it looks like it has 2, 4, 6, 8. And notice it is, it's going to be half of those, so it's 4. It's in family 5, so 5 minus 4 is a +1. This oxygen, this looks like it's got, what, 6 minus 1, because half of these, and then -6, so that's going to be a -1. And if I look at F, it's going to be 7 minus 1 minus 6, it's going to be 0. So all the F's are 0. So you got a +1 and a -1 here. If I go through and do things here, notice with the phosphorus, I have 5 minus 5 is 0. The oxygen is 6 minus 2 minus 4 is 0. And then this fluorine is going to be 0. So in terms of formal charge, this one is the better model. Okay, if you just talked in terms of octets, then this one would be the better model. So this one will be taken if asked to define this in terms of formal charge. Again, you might be asked to define something in terms of either octets, that would be preferred, or in formal charge, then this one would be preferred right here. Okay, the last drawing I'm just going to show is what if you get an ion? This is something we've drawn that has a resonance structure. It's really not going back and forth. It's just like a 1.5 bond here and a 1.5 bond here. However, when I draw these oxygens, I'll draw them like they're localized on a particular spot. Notice when I do things, I can say 5 minus 3 minus 2, the charge on oxygen 0, or I'm sorry, the charge on nitrogen 0. With the double bonded oxygen, that ends up being 0. And with the single bonded one, it ends up being -1. Now we know this is really a 1.5 bond, so I'm trying to put a localized electron where it really doesn't exist. But notice overall we get a -1 charge. Can that happen? Well, yeah, because we have a negative charge here. Now the thing I'm looking at in this structure is this last rule, and the last rule states, if non-equivalent fluid structures exist for a species, those with the formal charge as close as 0, and with any negative formal charge on the most electronegative atoms are considered to best describe the bonding of the molecular molecule or ion. So notice where the negative charge is on an oxygen, which is more electronegative than nitrogen. So that supports a better model than if we came up with the same type of model with the -1 on the nitrogen. So having the -1 on the more electronegative oxygen is a preferred thing. So this looks like probably as good a model as we can do in this case. All right, those are just some examples of formal charges. Hope that helps. Thanks for watching.